Your AI agent has a blind spot. It can only see the handful of things you paste into it. Everything else, the error that scrolled off your terminal, the slide from a call that already closed, the documentation you skimmed 10 minutes ago, is simply gone. You ask it what that build error was, and it has nothing to say. It was never watching, and it has no way to look back. That gap between what you just saw and what your agent knows is the whole problem. Now, you could screenshot everything you do all day and ship it off to some cloud service to buy that memory back. But think about what that means for the most private thing you own: your screen. So here is a different idea. A small server that gives your agent a searchable memory of your screen, that runs entirely on your own machine and never sends a single pixel anywhere. You may have seen tools that promise this before. Screen history that quietly remembers everything you looked at, and the problem was always the same nagging question: where does all of that actually go? This project answers it by turning the whole model inside out. It does not record a video of your day. Instead, every couple of seconds, it takes one glance at the screen. It reads the text in that glance using optical character recognition. And then, and this is the important part, it throws the picture away. What it keeps is tiny. Just the words that were on the screen, and a compact mathematical fingerprint of what those words mean. The reading, the storage, the searching, every single step runs locally on your own processor. No cloud bill, no telemetry, no terms of service to read. There is no account to sign into, no server in someone else's data center. Nothing leaving the building. And the agent reaches all of it through the Model Context Protocol, the same standard plug that already connects your other tools. Let's follow a single frame through the system. The recorder captures the screen whenever it notices a perceptible difference from the last captured frame. Now, most of those frames look almost exactly like the one before. The same editor, the same idle window. So a perceptual hash compares each new frame to the last and quietly discards the near duplicates. There's no point remembering the same screen 100 times over. And we can set a minimum time gap between captures to keep things efficient. Here is the tricky part. Taking a screenshot is fast, around 10 milliseconds, but reading the text inside it is slow. Sometimes 100 times slower. If you simply chain the two together, capture would freeze, sitting there waiting for the reader to finish. So the design decouples them with a single shared slot that holds exactly one frame, always the newest one. While the reader is busy working on one frame, a fresh capture just overwrites whatever was sitting in the slot. The newest frame always wins. Work never piles up into a backlog, and the moment you are actually looking at is never the one that gets dropped. And the instant the text has been read off a frame, the image itself is discarded. It is never written to disk. Not once. Your history is text, never imagery. So how does it actually read what is on your screen? It happens in two stages. First, a detector sweeps the whole image and draws a tight box around every separate patch of text it can find. Then a recognizer takes each of those boxes, one at a time, and reads it out, character by character. There is a clever detail buried in here. Terminals and dark code editors show light text on a black background, and that reversed contrast trips up most text readers. So when the engine notices a frame is mostly dark, it simply inverts the colors first, turning it into clean black text on white, and reads it perfectly. Now, once the words have been read, but before any of them are allowed into storage, the text passes through a redactor. This is your safety net. The recognized text is scanned for sensitive patterns: credit card numbers, social security numbers, passwords, and secret interface keys. And every match is swapped out for the single word, redacted. That scrubbing runs on the extracted text before it ever touches the disk, so the raw secret is never written down in the first place. And the list of what to catch is not fixed in stone. Teaching it to redact something new is as simple as adding one more regular expression to a config file. Only after that is the clean text turned into that meaning fingerprint, a list of 384 numbers that captures what the text is actually about. That fingerprint, the text, and a timestamp all drop into a local database. And that fingerprint is the key to everything that comes next. Now the payoff. Picture this. A few minutes ago, a build failed in your terminal. You read it, closed the window, and moved on with your work. And now it is truly gone. So, you just ask, I hit a build error earlier, but I already closed that terminal. What was it? Behind the scenes, the agent searches the screen history for the word error and pulls the failure back, word for word, from a dark terminal it could never otherwise have seen. It reads back the exact error code and the file and line it came from. Now here is the harder one. And the more impressive one. A slide from a video call is long closed, and you ask, vaguely, the way people actually remember things. What were the points on that planning deck? The one about scaling down the database. Notice that you never typed the words that were actually on that slide. But this is exactly where the meaning fingerprints earn their keep. A search by meaning finds a slide anyway, scoring it almost 89% similar to your question. And the agent reads back all 3 bullet points. The screenshot itself is long gone. Only the meaning survived. And the meaning was enough. There is one more sense on the roadmap for this. Beyond reading the text on your screen, an agent could read its structure. The operating system already knows what is a button, what is a text field, and which one holds your cursor. So a future version could hand the agent a clean list of the real interface elements, not just the flat wall of text, so it knows what it can act on and could plan a real click instead of guessing at pixels. And the same privacy rules would still apply. A secret typed into a field would come back only as the word redacted. Here is the part that is genuinely surprising. To give your agent this entire memory, you write no code at all. There is nothing to expose by hand. You add a few lines of configuration, one entry pointing at the Hybrid Vision MCP server, and that is the whole integration. From there, the agent connects to the server on its own. It asks what the server can do, and the server hands back its tools. Read the current screen, get the last few minutes, search the history, and on the roadmap list the elements on screen and even click and type into them, with more still to come. The agent now knows each tool by name, what it does, and exactly which arguments to send. All discovered automatically, nothing hard-coded on your side. And then it simply calls them, the same way it calls any tool it already has. Searching by exact keyword versus searching by meaning are not even 2 separate tools. They are the same tool, with one flag flipped. And underneath, the recorder constantly filling the memory and the server answering the agent's questions share one single storage layer. So the instant a frame is stored, it is already there, ready to be searched. No syncing, no waiting, no second copy. A config change on your side, a few hundred lines on theirs, and your agent can suddenly see everything you have seen. So that is the whole idea. Your agent finally gets a memory of everything you have seen. And it costs you nothing in privacy, because the trust is built into the architecture itself, not bolted on afterward. The pictures are deleted the instant the text is read. Sensitive details are scrubbed before they are ever saved. And not one byte ever leaves your laptop. The agent remembers what you were doing, and you remain the only person on Earth who can ever read that memory. If you want to run it yourself, the repository link is in the description.